Okay, it's lecture 7. Let's go to our lecture 7. Uh, this is the cross section of our FinFET assumed in ASAP 7. So maybe you can see many different structures, but for a while, just please concentrate on the shape of this part. So you can clearly see there are three fins, and when you have a look at these three fins, the height of a fin effectively is denoted as this length scale. No, this is the fin. Of course, in its structure, maybe you can think that this is the entire height of our fin, but effectively only the part beyond this level is regarded as the effective fin, because this relatively light gray is corresponding to STI. So shallow trench isolation. Shallow means that this depth is not that high. It's just in this case about 30 nanometers, something like that. And in reality, so the depth of this STI is more or less comparable to that of this fin height. So roughly speaking, we just make a certain height of fin structure, and half of it is filled with STI, and half of it is just exposed to the external world to be later covered by gate oxide. So this is the effective one, and as I told you several times, so although it has three different phases, so that's the reason why we call it as a tri-gate transistor. However, this one and this one shows much difference in its physical length scale. For example, in our ASAP assumption, this is about 7 nanometer wide. Actually, they assume 6.5 nanometer, but I will use just integer number in terms of nanometer. So it's about 7 nanometer, and here they assume that this height is 32 nanometer. So when you just make a simple comparison, you can easily find that the ratio is almost 4.5 to 1. So this is really narrow and tall fin. What is the trend? This is corresponding to the 7 nanometer technology, although it is shown here ASAP 7, but actually when the authors of this ASAP 7 PDK try to make this future prediction, they didn't make the improvement of a fin shape. It means that actually this 7 nanometer and 32 nanometer tall, this fin is actually the fin of our previous technology, like 14 nanometer technology, 22 nanometer technology. So they didn't assume that, well, maybe fin will be just kept as before and just shrink different parts. What is the reality? So yes, in reality, in TSMC, Intel, so at the 7 nanometer node, the actual height seems to be because usually in these days they do not expose or disclose the actual value of their fin shape. So we have to estimate the dimensions by TEM, image inspection. So however, it is known that its height at 7 nanometer technology would be around 50 nanometer. So also this thickness is, or width of this fin is getting shorter and shorter, so down to about 5 nanometer eventually. So maybe you can see that eventually we have the aspect ratio higher than 10 to 1, so 50 and 5, then this is 10 to 10 to 1. However, this height is even taller when we consider the last FinFET technology. So please note that in this ASAP assumption, we have made a relatively old fin technology. Our fin is not tall enough and not narrow enough compared with the real technology, but let's just live with it because ASAP 7 gives us a lot of information which is not available to us if we take other references. Okay, so now I think that I have covered the contents here. Fin height is 32 nanometer and fin width is 7 nanometer. Although in reality it was assumed as 6.5 nanometer, but you know our program is just integer numbered in nanometer scale, so we will just use 7 nanometer. And yes, this 32 nanometer fin is a little bit short, and STI depth is 30 nanometer. Okay, so now you can see this structure, and once we generate this fin structure, then STI will be filled and this part will be exposed. After that, here we will just cover this fin with high K dielectric and metal gate. Another consideration is the shape of this source and drain. Why do we have this kind of shape? So if we make a cut along our center of channel, then we cannot see this source drain. But this source drain is seen when we make a cut along source drain part. Maybe that is difficult to right now understand because we don't have a 3D measurement structure right now. So just please wait for a while. And simply speaking, our gate contact are located around this, and all other parts like LISD, PMD1, 2, PMD0, LIG, all kinds of these ones are corresponding to middle end of line or back end of line. So we will talk about them later. Okay, so simply speaking, we will use a FinFET. Its height is 32, although it is an old timer, but we will use it. That is one. Is there any noise? Oh. Okay. So now let's start our fabrication process. So first of all, we have to fabricate this fin structure, uniformly distributed fin structure. Do you remember our numbers? So fin pitch was 27 nanometer and the width of fin was 7 nanometer, and this fin pitch 27 nanometer is not directly achievable by certain lithography. I mean that of course when we use EUV, then it can be achievable. However, if we use DUV, so which has a longer wavelength than EUV, then this 27 nanometer pitch cannot be obtained. So today our main topic is how can we achieve this kind of short pitch lines out of much longer wavelengths. So although that is my presentation is quite much simplified, but I think that the rough sketch can be given to you by my lecture. Here, as I told you before, so my coloring is not that matched to material. So sorry about that. I will improve it. But right now, I'm assuming that there is a 100 nanometer thick substrate. So sorry about that. 100 nanometer is really an arbitrary number. Actually, substrate should be quite thick, like several hundred micrometer, not nanometer. But the deep substrate is not included in our emulation because they are not actively used. So that's the reason why here we have the reason named that the deep substrate having just 1 nanometer thick, and this 1 nanometer thick layer is a representative of our deep substrate. So all kinds of real deep substrate are just consumed here, so forget about it. And we are just observing just a surface of our silicon wafer. So in this case, what we do is like this: make a peroxide. This peroxide, or sometimes called as a sacrificial oxide, this is to protect our very precious silicon substrate. So its thickness depends on case, but I just maybe you can find out how I can find out these numbers. So although I was hired by Samsung Electronics for 2 years, however, this kind of number is not disclosed to everybody. So I have no idea how I found these numbers. I just search and dig out literature. So please do not consider these numbers as a definitive ones. So in reality, numbers can differ quite a lot. And also, so although I say that here mandrel region is 50 nanometer thick, however, actually, in order to realize this mandrel, also what is it? So I will explain later. Anyway, for realizing this region, actually we need more layers in it. Although I say that this is a homogeneous uniform one single layer, actually we need to insert some intermediate layer to improve attachment, and also we need another one, 3 or 4 layers are required to realize this one. But for why? Just forget about it and say that this is just a rough sketch about what happens in reality. Okay, so let me just come back. Now, although it is given as a 100 nanometer, it is just a shorted form of our deep substrate. And here we have a peroxide. Its value is about only a few nanometer. Actually, in order to make this structure, what you have to do in our Armstrong Craft code is deposit silicon dioxide with a thickness of 3. And in order to make this hard mask, you have to call deposit once again with a different region name and thickness equal to 80. And also you have to do once again with the thickness of 80. But in this case, hard mask, which is made of typically silicon nitride, and mandrel, typically made of amorphous silicon. So they are really deposited. Deposited means that it's like snowing. So you have your ground and snow flakes comes from sky and it is deposited. So ground is not changed, and you have a certain thickness of new snow layer. That is deposition. However, when we talk about this oxidation, actually it's not, it's like not snowing, but just like pouring certain amount of water into dry ground. Then what happens if you just pour certain amount of bottle of water into your dry ground? Then your ground will be made by two different layers. One layer is still quite dry, not wet, and on top of it you will have a certain wet surface layer. So this part is no longer dry ground, and you have a different physical layer which is called as a mud. So it's like oxidation. So although they are completely different in their physical mechanism or chemical mechanism, but in our realization in computer program, so we don't care about it. Just to say deposit with 3 nanometer. So simply speaking, it introduces on a little bit further discussion. So please be careful. Let's just say that this is the original line of silicon, our silicon surface. If we make certain deposition of, for example, silicon nitride on top of this silicon, then our new silicon dioxide will be located on top of this original silicon layer. So the interface between silicon and silicon dioxide layer will be still the position where original silicon. But if we consider oxidization, then actually some of our silicon part is converted into silicon dioxide. So where can you find the interface between silicon and silicon dioxide? So our interface can be found at here. And where is the end of our newly generated silicon dioxide? There is also the end of a silicon dioxide layer. So simply speaking, that will be the shape of a silicon dioxide layer. It consumes our silicon. The original silicon layer is converted into silicon dioxide together with oxygen sent from the sky, so the top part. So their interface move toward deep substrate. So actually, if we say that there was originally 100 nanometer thick silicon layer, and if we make oxidization with 3 nanometer, then roughly speaking, half of it is consumed. So the position of our silicon top will be no longer 100 in the coordinate, but it would be around 99 or 98 nanometer in this case. But in this calculation, we don't care about that one because we do not do exact calculation of process simulation. We just wanted to make a certain model shape of our structure. Please be careful about this limitation. And so that's the reason why I write down in this way. This is a thermal oxidation. That's thermal oxidation. So therefore, although silicon is a little bit consumed, but we will just treat it as a usual deposition. So now we have prepared 3 different layers on top of silicon. So here we have very narrow, relatively narrow PET oxide, and here we have a silicon, typically silicon nitride, and here we have amorphous silicon. Maybe you can find that we intentionally introduced different layers, different materials, and Yes, so although silicon nitride and silicon dioxide, both of them are insulating layers. However, they intentionally introduce differently because they have different etching rate to different etchant. So we wanted to have a selectivity for these materials. Okay, I will explain later if we have time. So our main concern today is how can we achieve this short pitch of 27 nanometer. Maybe you can ask me this question. Well, in reality, 7 nanometer technology, the realized fin pitch was not 27. It was about 30 nanometer or slightly even larger. So why we have to talk about 27 nanometer? But 27 was a little bit short in terms of 7 nanometer, but nowadays it should be achieved here. So 27 is not that much exaggerated value, so we have to talk about 27 nanometer. In reality, in order to realize this 27 nanometer fine pitch, we have to adopt this technique called as self-aligned quadruple patterning. So self-aligned means that they are, we don't have to do any further patterning. Once we pattern once, after that the later steps can be just relying on the initial pattern. That is the meaning of self-aligned. This self-aligned concept is quite important because if we do multiple lithography, then there is no guarantee that our two continuous exposure are perfectly aligned. For example,
Can you turn off the AC?
sorry.
Can you turn off the air conditioner?
Okay.
Thank you.
So now you can hear me better. So self-aligned means that we do only once for our lithography. Then once we do certain lithography, then we will have a pattern on our wafer. Then depending on that pattern, we wanted to do certain additional patterning using that existing pattern. This is the meaning of a self-aligned. It is so important because if we do two times of exposure, then you can find that there is no guarantee that they are perfectly aligned. For example, let's say that I wanted to make this pattern and this pattern and also here and there, let's say, and say that this sorry about that, so they are not uniformly placed. So let me just draw. So let's assume that they are uniformly distributed. After that, you feel that, oh, maybe this distance, for example, let's say that this is the pitch is 27 and pitch is 27. Oh, I cannot draw these lines with pitch of 27. So what you can do actually is, although I cannot draw lines with pitch 27, but let's assume that I can draw lines with a pitch of 54 nanometer, twice wider. So what we can try is draw this line and draw this line. Is it possible? Yes, we just assume that we can draw lines with a pitch of 54 54. Actually, please don't be fooled by my assumption. Pitch of 54 in reality is not achievable by our DUV technology. Actually, it is done, but it can be done with the EUV technology. So DUV is not possible. So that's the reason why we have to use SAQP. I will explain it later. But for a while, let's assume that we have a certain capability to draw a fine pitch over 54, but 27 is not possible. In this case, what we can do is just to draw lines with a pitch over 54. After that, why don't you just to try draw this line once again? How does it look like? So although we cannot make 27 nanometer pitch lines, but just to say that 54, and just to shift it the second pattern from the original pattern by amount of 27 nanometer and just to draw it. It can be a solution, and it is actually the solution, another alternative way we do it. So this one is called as LELE. I don't know how can you pronounce it, LELE or LELE. I'm sorry about that. But anyway, this technique is called as litho etching. Litho etching. So means that litho, first draw this 54 line, and etching means that really patterning. After that, once again litho. This second litho is for the one shifted by 27 nanometer and litho etch. This kind of technique is actually being used in industry, but think about the potential problem of this technique. You can draw 54 lines, pitch 54 lines quite well. That's good. However, there is no guarantee that your second line is exactly separated by 27 nanometer from your first drawn line. Let's say that unfortunately you have a margin of, for example, 2 nanometer. So the distance between these two lines becomes, unfortunately, 25 nanometer. Then what will happen? The distance between these lines becomes 25 pitch, but the pitch between these two lines becomes just 29. So because we have just lost 2 nanometer, and that 2 nanometer is added to the other part. So that's the reason why if we make such a kind of misalignment between one patterning and second patterning, then it will introduce non-uniform distribution of your fin lines. Is it good for your later fabrication or not? Certainly it is critically bad one, because everything our next steps are based on uniformly placed fin patterns. So but this LELE is actually being used in reality. It means that our engineers, litho engineers, are quite good to control the margin or misalignment of our two litho steps. But anyway, we wanted to reduce such kind of a potential problem of misalignment. Self-alignment can remove that difficulties by just using only one single exposure. Then based on that pattern, we can try to make it. Also, let's go to the more details about this technique. Although in reality we are using SAQP QP, quadruple patterning, but today I will show you just self-aligned double patterning. Then question is, can we really make fine feature of 27 nanometer using SADP, self-aligned double patterning? So it's not. We cannot do that because, as I told you before, our capability to draw 54 nanometer pitch with DUV is not existing. Sorry. So instead, we can draw lines with a pitch of 108 nanometer quite well. This is not that difficult and it is impossible. Okay, simply speaking. So that's the reason why starting from 108 nanometer pattern, we reduced this you can say pitch 54 and do it once, then we will have eventually pitch of 27 nanometer. That is the situation of quadruple patterning, but we will just assume that we have some magical way to draw 54 nanometer pitch lines. After that, do it only once. Oh, sorry about that. Do it only once to reduce it to 27. So please be careful. This is not that realistic. Well, anyway, in this case, we must draw lines with a pitch of 54 nanometer. Let's assume it. We can do it. And here we have a certain specification. Although the spacing, the pitch between two pattern is 54, but duty is not 50-50. We wanted to make width of 24 nanometer and spacing is 34 nanometer. Of course, some becomes 54. However, although we have this line, but relatively narrow, and the spacing becomes 34 and width is 20. Why we selected this number? Why don't we just go to 27, 50, 51? Then that introduce once again non-uniform distribution of our lines. I will explain it later, but for a while, just believe me, and this spec is used. This selection is usually called as trimming. I'm not quite sure we have to have once again M or not, but anyway, this is called as trimming. We carefully select the original pattern to match the final uniform spacing. So how can we realize this patterning? Up to now, we have no idea about how can we make a pattern in our Armstrong Craft code. So I will show you the way. Here we have a new statement in Craft. So this is not top statement, but it should be called within our Craft statement. You have a Craft statement and you call multiple depot statement, and this mask should be also in the same level. So here we have a mask, and you just define mask. When you do this job, then actually there is no changes in our structure. This is just preparing a mask. Later, this defined mask will be used for our deposition and our etching process. However, this is just a declaration of a certain mask. And as usual, we can specify its name, and Lx and Ly should be equal to those of our Craft system. So here we have 162 and 288. this is corresponding to our original specification 162.288. What happens if I say 8, 8? So instead of this one, if I say 8, 8, at this stage there will be, I'm not quite sure, but there will be no error, but it does not work properly. So please manually set your Lx and Ly values to match that of size of your entire system. Okay, then as its body, it can have multiple rectangles, and these rectangles just specify two coordinates x0, y0. This one represent a point, and x1, y1, this one represent another point. And by its definition, we assume that these 2 points are 2 diagonal points of our rectangle. So let me just do it. So 0, 26. So let's just say this is x and this is y. Then here we have 0, 26. And how about our next point? 162, 46. Here we will have 162, 46. It means that we are now talking about a rectangle whose width is corresponding to 162 and whose height is 20. So we are now saying that, oh, there exists a certain masked layer or region whose shape is given as this form. Okay, now you can see the second rectangle, and this second rectangle has the same x0 and x1, only y-axis coordinates are different, 80 and 100. Then if we have 80 and 100, still its height is just 20, and this is 80 and this was 46, and the difference is given as 34. So now you can see that these statement of these 5 rectangles just shows 5 masked layer, and they are, each of them are separated by 34 nanometer. So spacing over 34 is implied in this implementation, and its thickness 20 is given by this specification. So please try to type this argument into your own input command file, and please try to learn it. Then, of course, as I told you before, defining mask does not change your final structure, but together with this mask and etching or deposition, you will have a different result. Okay, now we define 5 different rectangles and specify one point and another point, and they are working as 2 diagonal vertices, and these rectangles are masked, means that they are avoided from etching or deposition. So they are masked. It means that if you have, for example, this pattern, yes, this part is masked and this part is unmasked, and when you call this etch statement, what will happen? This one survives and this one goes away. So please understand this convention. Well, maybe you can ask me, why did you define in that way? How about the other way around? this masked part is etched away and unmasked one survives. It is related with the current popularity of positive PR. PR means that photoregister. This positive means that when it is exposed by the light, then its chemical structure becomes weakened and eventually it can be washed away. So this kind of positive PR is widely used in these days. So masked part, this part is saved from exposure. So this part, masked part is actually corresponding to unexposed one, and this unexposure means that the chemical structure of our PR is photoresistor is still strong and it can survive. So that's the reason why I adopted this convention. But of course, depending on the situation, we can change it. But right now, our implementation looks like this. Then, sorry, I think that I have to change the title of my slide, this slide. So sorry about that. But anyway, now we have done the etching. So etching and thickness. So if you call the etching without this mask specification, then you will just have the uniform etching along G direction. So in this etch statement, the basic behavior is G directional etching. Then how about isotropic etching along X direction, along Y direction, along G direction? Maybe we can think about the uniform etching. I mean that it's like this. Say this is PR, photoresistor, and for example, let's say this is a silicon. If we adopt, for example, anisotropic etching, then our silicon layer will show this kind of evolution in its boundary, because this part is protected by our photoresistor and we have a strong anisotropy, only preferring the G directional evolution. That is anisotropic etching. But there is also isotropic etching. If we have isotropic etching, then the shape will show a little bit different behavior. It means that now we will have this behavior and this behavior. Yes, underneath of this PR, which is originally protected by photoresistor, but it can be etched away, because from this point, for example, from this point, even this X or Y directional etching can be possible. So we will have this kind of rounded shape in our etching profile. So how about our Ångström-Kraft code? So isotropic etching is under development, so please wait for a while. But today's lecture, we don't have to have isotropic etching. We can live with only anisotropic etching. So yes, that's the point. I mean that what we have in reality, please don't be confused about this kind of graphs. If you just naively believe this graph, it looks like by doing certain, how can I say, certain photolithography, we can just make this pattern immediately. However, in reality, what we have to do is like this. Let me just draw once again for your understanding. Let's say that this is a silicon, and here we have very narrow pad oxide, and now we have silicon nitride, and here we have mandrel. Okay, now this is amorphous silicon. We cannot make any pattern directly to this amorphous silicon. So what we have to do is, in reality, just to make another layer of photoresistor and expose it to certain patterning. So say that now this part is exposed and this part is also exposed and this part is also exposed. So as I told you before, if we use positive PR, then by exposure this part becomes quite weak against this washing process. So now when we just develop it, develop means that washed away this weaker part, then we will have just shapes like this. That will be the remaining shape. After that, we have to do once anisotropic etching. So for amorphous silicon, the etchant which can selectively etch only amorphous silicon and do not touch the underlying silicon nitride. So a certain etchant can etch amorphous silicon quite well. However, when it hits this silicon nitride layer, suddenly it becomes quite slow. So that is the magic to make the transfer of our PR pattern onto this amorphous silicon. So I'm not quite sure I have delivered the main point quite well or not. So simply speaking, the only thing we can do with patterning is PR patterning. Photoresistor can be patterned. After that, the transfer of drawn pattern into other material should be done by etching process. And in this etching process, we prefer to have anisotropic etching. So selectively etching only amorphous silicon and do not etch silicon nitride, then after this action, now we have a certain structure looks like this. This is the one you are looking at in these graphs. So I will use this kind of convention in many times. So therefore, maybe you can get some misconception like we can pattern our material, any material, by drawing certain masking. But please be careful. Whenever we say patterning, that can be done only on our photoresistor. It means that this step, so introducing PR layer and exposing development and etching, that is understood in our consideration. So although we can say quite freely pattern it, but inside it actually we have so many internal steps before doing this kind of thing. We have to certain pre-cleaning, and after this exposure also we have to do another post-cleaning. There are tons of steps in it, but well, just assume that can be done by somebody, not ourselves. So now we have this pattern. Then please have a look at this size. So although the size is not explicitly shown here, but you know, this guy is 20 and this guy is also 20 and 20, 20, 20. We have drawn 5 unmasked, masked layer, and they survived. And their spacing is also 27. So now we have 27. So since spacing is 27 and width is 20, these lines have a pitch of only 54, which is twice larger than our wanted pitch of 27. Then how can we make this fine pitch, twice shorter pitch out of this original drawn pitch? That is the magic of our double patterning, self-aligned double patterning. So this is the way. Here we deposit a certain amount of silicon dioxide. So please note that once again, this is silicon nitride, and we intentionally use a different material, and we are assuming that we can find a good etchant who can quite well distinguish silicon dioxide and silicon nitride. For certain etchant, it can selectively etch silicon dioxide quite well, but does not etch silicon nitride at all, or with quite a low etch rate. Virtually no etching happens. And here important number is 7 nanometer. You can find that this 7 is corresponding to the desired fin width. So deposition thickness is corresponding to our desired fin thickness. For example, if we wanted to have a wider fin, then actually we have to increase it, and if we wanted to have a narrow fin, actually we decrease it. So now we have anyway deposit our 7 nanometer thick silicon dioxide. And you know, in this case, in deposition, if we do not specify anything, then actually we are calling isotropic, sorry about that, isotropic deposition. So maybe you can ask me this question. Well, actually, the basic behavior is anisotropic depo. The basic behavior is isotropic deposition. Why do you introduce such kind of confusing convention? Oh, it is only because this code is under development. So I will make a uniform convention later, but right now please accept this stage. So that's the result of our isotropic deposition. This green line is corresponding to silicon dioxide, and please have a look at its shape. If we, for example, if we try to do certain anisotropic deposition, then what will happen? If we do a really anisotropic deposition, then our final deposition will just look like this one. So you can easily understand, if we deposit something on top of the surface, then this side wall is 100% perpendicular to the direction of deposition, and we don't have any deposited material. Please think about a certain building. Yes, we have a certain building and it snows, after snow is over, then how does it look like? On the roof we have snow, and ground we have snow. But do you expect sidewall? So when you go to the office, your entire office is covered by a thick snow layer. You don't expect it because this is the normal surface of this building is quite much perpendicular to the direction of deposition. So this is an isotropic one. However, please think about a different state. So a certain day, although it's snow, but also it winds quite well. So it's the motion of a snowflake is no longer like this unidirectional, but snowflakes are just hanging around and just attached to the sidewall. Then what will happen? We will see just quite a conformal behavior of a final deposition profile. So that's the reason why when we perform this isotropic deposition, we expect that our final shape looks like this. If it is really isotropic, then please try to measure the thickness. Here we have a thickness that will be 7. And how about this? Here we will have a 7. And here we will have a 7. Okay, great. But point is, in this case, is how thick is it? If this is really isotropic, then it would be 7 nanometer. In reality, is it really 7 or not? So it really depends on your material. So if you have a certain process, then you can have a really 100% of the thickness. And you know, this amount of anisotropy really depends on material composition and other process conditions. But in this case, we just assume perfect isotropic deposition. So you can expect that even along this side wall, you have 7 nanometer thick sidewall growth. This is the point. Okay, so therefore, starting from its growth origin, starting from here, it is 7 nanometer. And starting from its growth origin, it is behaving or advancing 7 nanometer. Yes, it is quite true, but point is, if we measure from the initial level of silicon nitride layer, so height of this layer is this newly generated silicon dioxide layer. The height is almost close to that of this mandrel layer. Mandrel layer was deposited with 50 nanometer. So we will have sidewall layer whose height is about roughly 50 nanometer and whose width is about 7 nanometer. Although it is not looking like a perfectly shaped square in this case, because it is generated from sidewall deposition, its shape looks like this. So this and that are not symmetric. They have a certain tendency to attach to this part or that part. But anyway, point is, its width is 7 nanometer and it can be controlled by our deposition precisely. And its height is also can be controlled by our initial deposition thickness of a mandrel layer. So that is the point. So please, now we have done isotropic deposition, and next step, this is the key. etching is done. However, this etching is anisotropic etching. So by doing so, previously our shape looks like this. But this 7 nanometer, original 7 nanometer is gone by our anisotropic etching. And of course, our top part, this part, is also gone. So compared with the original shape, this part is also a little bit etched away. However, since its thickness is about 50 nanometer, so 7 nanometer etching for this short distance doesn't make its stability. We have still well defined this layer. Okay, so you can just call etch thickness equal to 7, and it will try the anisotropic etching only along G direction without any mask. So we don't specify mask here, so we will have entirely eliminate the shape of our materials. So simply speaking, we have remaining side wall, and this remaining side wall is actually used as the pattern for fin. So they have the thickness of 7, and their spacing is defined by 20, the original thickness of our drawn pattern. So that's the reason why we intentionally select this way to 27. And let's talk about the impact of trimming. Well, at the beginning of our drawing of a 54 nanometer side, let's assume that we become quite lazy. Oh, just to do 50-50. So we just draw 27 line and separated by also 27. Yes, this is 27 and this is 27 and also this is 27. Let's say that this is our original structure. Then now we make side wall. Please try to draw your side wall just attached to your original pattern. Your mandrel, nearby your mandrel, you have a 7 nanometer side wall and 7 nanometer side wall and 7 nanometer side wall and 7 nanometer side wall. And after that, this red one, mandrel, will be eliminated. After that, when we just measure the distance or spacing between these lines, you can find that this is just corresponding to number 30. Because, you know, although they have 27 nanometer away, but these two patterns are generated from the same side, and they are become closer. And how about the distance between these two lines, this and these two lines, and the spacing becomes 27, the original thickness of our drawn pattern. So simply speaking, when we finish in this way, then although overall they are separated 27 nanometer in its average value, but our lines will have just long distance, short distance, long distance, short distance. That will be the final result of this naive pattern. So this kind of a 50-50 strategy cannot be done. So we have to carefully select the original drawn lines, and that is called as trimming. So of course, although we say that we can use, for example, this specification, width equal to 24 and spacing over 34, then we can make a uniform spacing. But it is just a naive calculation. In reality, we have to do a lot of repeated exercise. Make it, and it becomes non-uniform. Oh, then I have to change it a little bit. So that's the reason why we have a separated team for this lithography and make a very uniform pattern of our fins. Please note that this uniformity of our fin line is one of the most important one in our fin pad fabrication. From the beginning, if they are not aligned uniformly, then every step later will make a certain hidden difficulties in the realization. Okay, so now the next step, of course, will eliminate only this mandrel. So mandrel is once again amorphous silicon. So in this case, we have to introduce a certain etchant which do not attack silicon nitride, which do not attack silicon dioxide. Only silicon is etched away certain material, and then the remaining part will be so the same pattern without mandrel. So let me just draw once again. Then we will have certain patterns, and their pitch is always the same to 27. That will be our final fin patterning. Well, up to now, what we have done is the patterning on top of this peroxide silicon nitride, and here we have a patterned one. So actually we have to this pattern onto this silicon substrate, otherwise that is meaningless, because we wanted to make here fin and here once again another fin. That is our original intention. So as you know, we have to do once again certain anisotropic etching to realize this shape, but it will take the next lecture. And you know, please note that although we are considering just a part of it, but if we remember the layout of our original structure, then we have to have a certain layer where only fins are surviving, and for other parts we have to actually eliminate fins. Then how can we eliminate fins, unwanted fins? And there are some options, but we will take the option provided by AS87, and that will be explained in our next lecture. And let me conclude my lecture with a homework announcement. So here we have homework number 7. Usually I make a certain quite a continuous number, but we have no homework 6, no homework 5, so I will just align it to our lecture number. Lecture, if we have a lecture 7, then homework will be named as homework 7. And please submit your report by Monday morning, just before starting our lecture. And of course, the bottom line is you have to do your own exercise when you come back your room. So in front of your laptop, you have to follow all of this exercise I have shown you, and I intentionally hide my input file. So although I gave you the very beginning startup kit, but I do not give you the final one which can generate this shape. So what you have to do is, of course, I have already shown all code snippet in this slide. You can just type them into your file and just run step by step manner. That is my strong recommendation. Just watching the video or my lecture and my screenshot, it works. I understand. It doesn't give you the concrete understanding on the matter. You will find actually in reality it's not that easy to make this kind of shape. And if you make any mistakes in mask specification, okay, so let's say that if you make a typo here or typo there, then completely your result will be demolished. So please do your own exercise. This is the bottom line, and it is not included in your homework assignment. My homework is more fun stuff, so please, by using the Armstrong craft code, please draw your own alphabetic letter. So in this case, I have prepared my own F in this case. You can see that I originally make a very narrow and tall structure and define certain mask for this F shape by overlapping 3 different rectangles here and there, and another one I just make this mask. After that I etch the entire structure by amount of 50 nanometer. The entire structure was 100 nanometer tall, and I just etch its half thickness, so 50 nanometer etching. So that's the reason why we have this quite interesting F structure. I do not ask you to follow my approach. You have a tool. You have a tool, and please try to make your beautiful letter. So not only single letter, maybe you can write down your name, not only English alphabet, or you can just write your own Korean letter or your own language. What is your alphabet? What is Cyrillic? Cyrillic. Yes, maybe you can try it, although I cannot read it, but I will be very happy with that new character. So anyway, the reason why I'm asking you this seemingly unrelated to our FinFET is, please be familiar with our Armstrong craft and use of this mask structure. You can do it. So please, I wanted for you to be artistic guys about this homework. Okay, do you have any question about today's lecture? So simply speaking, today we have thought about SADP, self-aligned double patterning. However, in reality, we must adopt SAQP. SAQP means that once we have this pattern, then do it once again. This side wall is now working as another mandrel. So then you can make an even narrower structure. Actually, we start from 108, much wide one, and reduce it to 54. After that, it reduced to 27. So that's the reason why we call it as a double patterning. Okay, so I think that's it for today's lecture. And if you don't have any question, then let me conclude my talk. Thank you.